Welcome to qnawire.
So we first need to find the tension in these strings because both strings have the same tension. So we should first find the linear density. So linear density mu is simply going to be the mass over the length of the string. We know that this is going to be 8 times 10 to the negative third. 8 grams is simply 8 times 10 to the negative third kilograms. And then we're going to divide it by our 35 centimeter string, or 35 times 10 to the negative second meters. And we find that the linear density here is going to be 0.02285 kilograms per meter. At this point, we find the velocity. So the velocity can be found by the square root of the force tension divided by mu. And in this case, it'll be mu sub 1. So we can manipulate this equation and we're going to solve for F. So we can say F is going to be equal to V squared mu sub 1. And we know that V, as an aside, is going to be lambda F. So we can say V is going to be equal to the wavelength times the frequency, and then we'll square this, and then times the linear density. And at this point, we can then make it a little bit easier. We know also we don't have a wavelength, so we're going to have to actually find the wavelength by using this relation. This is just going to be the wavelength of a transverse wave. So it'll simply be 2 times the length of the string. So this is going to be 2L, and then it'll be F squared mu sub 1. And then we can say that this is going to be equal to 4L squared F squared mu sub 1. And then we finally have a tension. So we can say F is going to be equal to 4, and then the length of the string is again 35 centimeters, or 0.35 meters. We're going to square this. We have the frequency is given, that they want the frequency to be 262 hertz. We're going to square this, and then we plug in the linear density that we found, so 0.02285, and then we can plug this into any calculator, and we have a force tension of 768.8 newtons. Now, at this point, they want to find the mass of the second string such that it will have a frequency of 466 hertz, or A sharp. So we would first, of course, start off with the velocity, and this is going to be equal to the force divided by mu, and we'll say that this is sub 2 because we're dealing with the second string, and mu sub 2. Let's solve for this because we don't know the linear density of the second string, so we'll do F over V squared, and then this will be equal to F over lambda times the wavelength times the frequency squared, and then we can say that this is going to be equal to, again, the same thing as the previous slide, 4L squared S squared. That will be our linear density of the second string. So at this point, we can then use the actual tension that we found in the previous part of the problem, 768.8 newtons, and then we'll have 4 times 0.35 squared, and then we want this to have an A sharp sound. We want this to have a frequency of 466 hertz. This is the frequency of A sharp. So we can just solve this, and we have 7.22 times 10 to the negative third kilograms per meter. At this point, we can simply find the mass of the second string by multiplying the linear density times the length of the string. And we have 7.22 times 10 to the negative third. And then the length of the string would be, again, 0.35 meters. And we have that the mass of the string is going to be 2.52 times 10 to the negative third kilograms. Part C is asking us to find where should the fret be placed such that the first string now has a C sharp, is playing a C sharp, and that's going to have a frequency of 277 hertz. So again, let's find the velocity. This is going to be F over mu1. We have the linear density of the first string already, which is good because we can just simply substitute this in here. 768.8 divided by the linear density of 0.02285. And we're going to have a speed of 183.4 meters per second. At this point, we can say that the speed of propagation equals the wavelength times the frequency, and we'll solve for the wavelength, and this is going to be the speed of propagation divided by the frequency, and we'll have 183.4 meters per second divided by that frequency of 277 hertz. And at this point, we find that the wavelength is equal to 0.662 meters. At this point, we can find the length because we know that the wavelength is going to be equal to 2 times the length. So we'll have the length is equal to the wavelength over 2, and this is going to be 0.662 divided by 2, or 0.331 meters. And then the length of the string will be 35 meters minus this length. So, or 1.9 centimeters. So this is where we're going to put the fret. That would be where the fret is, 1.9 centimeters. And then at this point, we can find the part D. And part D is asking us to find the frequency of the second string now that we have the fret in place at that x coordinate 1.9 centimeters. So we can say again, V equals the force divided by mu sub 2 now. We're talking about the second string. And this is going to be equal to 768.8 newtons. And then we'll have this divided by 7.22 times 10 to the negative third kilograms per meter. And we'll have a speed of 326.31 meters per second. Again, we know that the speed of propagation equals the wavelength times the frequency, and we're trying to find the frequency, so we'll have frequency is equal to the speed of propagation divided by the wavelength, and we'll have a 326.31 meters per second divided by the wavelength of 0.662 meters that we found in the previous slide. So at this point, we can say that the frequency, and we simply have to evaluate this, and we'll have the frequency is equal to 492.9 hertz. And that will be your answer for part D. And that's the end of the solution. Thank you for watching.